machine if you want, but it'll look like this. So it won't actually have any notebook open. And what I did is I just double-clicked over here on the 01 notebook, which has kind of the intro. So we can talk about this stuff a little bit and get set up. So in terms of, so like I said, this is a great class for kind of Q&A and discussing kind of problem solving. So this is not a kind of class where it's like, we're going to learn how to do this exact one task with this exact tool, and then we're going to use this API, and then we're going to do a lab, and then we're going to wrap up. There are lots of classes like that, and those are great. But this one is a little bit more kind of wide-ranging and might be a little bit more useful if you need to make decisions about what tools to use, if you have to like collaborate with your coworkers on designing systems, if you need to kind of be thinking about, where your pain points are today and where they might be next year, and what things are worth changing and what things are maybe not worth changing, because change is never totally easy with these systems. So we'll talk about a bunch of things like that. Formally, we've got about 4 hours, a little bit less, end to end here. And I understand that's a long time to be staring at a screen, especially these days when many of us working kind of online and we have all these online meetings. I totally understand. It's really exhausting to kind of stare at the screen and you're listening to this disembodied voice and maybe clicking through code. And in your other window, your boss is asking you if you've finished something, or maybe you've got pets or kids around. So we will take a break for about 10 or 12 minutes at the top of each hour. That'll give you kinds of tools in the past. So these might be databases way back. They might be things like Hadoop. They might be things like Apache Spark. They might be, other more recent tools. If you've worked with any of those things, then you know that the last few years there's been quite a bit of kind of turmoil, right? There was a period, in the early 2000s up through the early 2010s, when the kind of Hadoop platform was kind of where, in industry anyway, it's where people focused most of their attention. And then we saw the rise of things like Apache Spark, right? So then for a bunch of years, the idea was, maybe we can replace all that stuff. Maybe not all of it. But we can, there's a question about boosting up the font. Yeah, let me crank this up. I may have to turn it back down when we do some codes because it may scroll a little bit, but so hopefully that is useful. I've got this up on 125% here. Hopefully that's a little bit clearer. And then, of course, you have the local copies, so you can see some of that stuff too. But hopefully this is good. So there were a few years where we had the story of, if you just learn Apache Spark, and you need a few other pieces, right? So Hive, Metastore is still around. We'll talk about that. Things like Apache Kafka. Of course, there's other queuing systems, but that was kind of or it still is to some extent, kind of the dominant tool there. So Spark is not the solution to everything, but for a while there was the story that if we can port all of our workloads to Spark and kind of focus on getting that right, that'll solve all of our problems. And that lasted for a few years, like a lot of hype cycles do. And Spark is a fine tool. I use it a lot. I'm not against Spark, but after a few years, you may have noticed, if you played around with this, and if you didn't, you're lucky, that there are some limitations, right? There's some things that Spark does really well. And there are some things that Spark doesn't do particularly well, especially around machine learning and AI, right? So when folks were just talking about collecting huge amounts of data and doing like ETL and analytics kind of work with data, Spark could kind of cover all of your needs. It's actually, a little tricky to learn and tune, but it's a really nice tool. But the more companies started thinking, well, to get the value out of this data, we don't just want to have it or do basic, statistical analysis. We want to actually use this to train machine learning models, build some kind of AI, empowered tools, even very modest ones. The more we got into that, kind of the more it seemed like, well, Spark's got some limitations, right? We're not going to throw Spark overboard. It's still really useful, but it doesn't really handle some of those cases well. So a few years ago, probably as we started getting into like 2018, 2019, towards 2020, there was kind of a question of, well, how do you put together one of these systems? If you're going to need more than one tool, that, kind of changes the picture a little bit. right? It's definitely a different world from just install the Hadoop distribution that your company has and figure out how to do it, or just install Spark or whatever. So that's kind of what inspired this class, right? And this is 2020 because this is really when this kind of reached critical mass, this challenge. Now, things are actually a little bit better now, and this is a really interesting time to do this class because, for a couple of years, 2019, 2020, it was, we had to do a lot of work to figure out how to solve these problems. And in the last year or two, some clarity has started to emerge from the haze about maybe what we might want to do next. That's a little bit less risky. We can see some things now, and there's some, to be more precise about it, there are some newer tools and newer developments in the last year or two that are starting to make this problem easier again. So that it's kind of a nice time to talk about this because instead of just saying, hey, there's a huge problem, we can now say, well, there's a challenge, but we've got some better guideposts about the way out of this challenge today. So just to kind of summarize what we're talking about, kind of end-to-end single product platforms are no longer the leading options. We'll see that probably the most promising single product style tool going forward, which is the Ray project. Even the Ray project is not really a single product end to end. We'll see that the Ray project handles certain things kind of within a really nice unified set of APIs, but it also brings in lots of other tools. So, and we'll see examples of this, but integration might be starting with some Spark data and then feeding it into Ray, or starting with some task graph in Dask that's supposed to retrieve data. And we'll talk more about these tools in a minute, and then feed that into Ray. Or take your data in Ray and then plug it into a Hugging Face hosted ML model. Right, so even kind of the most promising single product sort of platform tool, which probably is Ray these days, is not really this kind of walled garden single universe that we saw in the past. Right, so things are kind of changing a little bit there. So concretely, and we kind of talked about this kind of a little bit in this intro, right? We need to go beyond things like just, Hadoop and Spark, right? We want to look at some of these other tools, right? So things like Dask, things like Ray, things like Horovod, of course, TensorFlow and PyTorch, and, still keep some of the key pieces around where there isn't a clear replacement right now, or where the existing tools are state of the art. So, SparkSQL is probably still, well, I guess Presto is right up there, but I would say, Presto and SparkSQL are kind of state of the art in terms of using SQL over data lakes or lakehouse architectures. So we want to keep that around. But we also are going to want to figure out kind of when to kind of move from that Spark operation into something else, right? So SparkSQL is super strong, but just to kind of follow on what we were saying before, Spark ML, for example, has kind of fallen a little bit, maybe a little bit out of favor. It's maybe not as valuable as it might have seemed 6 or 7 years ago. We don't use Hive, the Hadoop SQL tool, so much anymore. I mean, I'm sure it's still running in lots of companies. We don't use Hive as much, but a lot of companies still actively using the Hive Metastore. So the Hive Metastore is still the de facto data catalog in a lot of big companies, just because it takes so long and it's so risky to change that stuff. So that may change in the future, but we still have to worry about things like that. And we have lots of orchestration tools, right? Probably the classic one is still Apache Airflow. There's other ones kicking around, things like Prefect, or even within frameworks like Ray, there's like an experimental component called Ray Workflow. But the Apache Airflow is still a big piece of that. So we're kind of trying to figure out how to mix the best of breed tools for different areas while still keeping the best stuff that we've got. And that's a little bit more challenging than just acquire and install one package, learn one package, and do everything there. So In this class, we want to talk about kind of the problems and the solutions there. We will do, code examples and look at some example use cases, but really we're trying to look at which tools make sense where, the flavor of APIs, meaning like kind of what it's like to use these different tools, what level of abstraction they operate at, so that you can be confident if you're recommending something, roughly how that architecture will fit together, communicating about them, migrating away from legacy systems. If you have a chance to do that. We're not really going to go super in depth on any specific tools, right? We only have a few hours, and we've got at least 3+ kind of very complex tools here. So we'll look at some examples. We're not going to go super in depth. I'm also not here to sell you on any specific open source project or product. There's a lot of things that go into those selections, and I think all the tools we're going to talk about have their strengths and weaknesses. So it's not about saying, well, forget this tool, it's old and no good. It's more about saying, well, this tool, maybe we want to focus on one part and not another, and then bring in some other tool for the other piece. In terms of the history, we kind of talked about this, so I don't need to maybe talk about that all over again. And I also won't read you this blog post, but you may want to take a look at it at some point on your own. It's from a couple of years ago, and it's an O'Reilly Radar piece on kind of best of breed. And it kind of makes this case for why the single tool that kind of claims to do everything is maybe not a compelling story at the moment. So we have a couple of kind of informal surveys. Like sometimes I've done this using like a survey that we set up, and there's like, numerical results. But for, what size data set you work with, feel free to just throw in the chat, things like roughly what size data sets. So, order of magnitude. Are we talking about, a gigabyte, 10 gigabytes, a terabyte, a petabyte? Where's most of your data stored? And again, like kind of in general, is it in the cloud, in some kind of blob storage like Amazon S3? Is it in relational databases? Is it in NoSQL databases? Whatever is interesting for you. So like, for some folks, it may be the size of the data set is what's interesting and not the storage. So in other words, it's not a test. You don't have to answer all these questions. I'm not gonna make anybody do that. How do you get data out of your data lake or lakehouse design? So assuming you have one of those, which most companies have at least some data in a sort of a data lake or lakehouse, how do you extract that data? Is it Spark? Is it Presto? Is it something else? And what kind of tools do you typically use for feature engineering and modeling? And for these questions, I know there's a lot of answers. So kind of again, like what do you spend most of your time doing, or what's interesting for you? It's not, we don't have to, we're not going to collect our resumes or LinkedIn profiles here, so you don't have to put down like every single tool that you use, but just the ones that are kind of dominant. So I'll kind of slow down here for a minute or so and give folks a chance to throw some of those thoughts in the chat window. And just so you know, I and the other folks here, we can see your initials in the chat, but I'll wait like one more minute. Okay, we've got a couple of data points popping up. Have any context, that might seem really big or it might seem really small. One of the things that's really interesting that's affecting this whole problem space is kind of captured in this chart here. And this I have to be thankful to Andreas. I think it was Andreas Müller, who is one of the maintainers of scikit-learn. And I owe this insight to him because he gave a talk a few years ago where he said, one of the reasons scikit-learn has become so successful was, and of course he could have said, well, because it's his code and, he's proud of it, but, he's a very modest person. So he didn't say, hey, I'm doing a great job with my, well, it's not, with the community's library that he leads. what he said, what's really making a big difference here is that as time has gone by, what everybody expected to happen in the 2010s was that over time, the data sets we'd be working with would be getting bigger and bigger. And what he said is that if you look at this poll, so this is, I have on here the 2020 version. I think when he first mentioned this was 2018, and if I don't have the latest numbers, but when I've seen them recently, it follows the same pattern. So the same pattern is still true. What he basically said is everyone expected that over time, data would get bigger and bigger. And therefore, we keep needing these more and more powerful tools to handle enormous amounts of data. But in fact, that hasn't happened. It's kind of a little bit of a surprise. So that this distribution, which is in this picture here, has more or less been stable for almost 10 years in terms of the distribution of data set sizes. So you can see that kind of the big bulk of the mass here is, somewhere in the 1 gig or 10 gigs up to maybe 100 terabytes. And then there's a little bump at the very end. So there are folks who are at the FANG kind of companies. If you're working at Meta or at Google or something, then yeah, you're probably dealing with, or working for a government, you're probably dealing with over 100 petabytes of data. But for most kind of applications in most industrial sectors, the data set sizes haven't gotten bigger, but compute power has gotten bigger. And so what's happened is that we could do more and more without as many machines, right? So, the thinking in 2010 was, man, you're going to need to learn this clustering tool and work with 100 or 1,000 machines. And by 2020, you're going to need 10,000 machines to get any work done. But it's actually been kind of the opposite. That as machines have gotten bigger and bigger, so for example, there's an instance on Amazon, I think their largest instance last time I checked had 20 terabytes of RAM and 300 something cores, right? So that single machine, is more powerful than a lot of clusters were several years ago. And even pretty, average servers these days, might have multiple terabytes of RAM, might have, a couple hundred cores. That's not unusual at all. So you can do a lot more without having complex clustering architectures. And that actually makes this whole thing even more complicated, right? Because sometimes we need clusters, or sometimes we don't need clusters, but we want them because we want to be able to finish some computation or some modeling task faster. Then other times we don't. We don't actually need that at all. We'd rather have the simplicity of a single machine tool, and we're willing to let it run overnight, or some kind of a batch job where we don't actually need to worry too much about absolutely maximizing performance. I'm just looking at some of the additional notes in the chat on tools that folks are using, and that's thank you for that. That's really cool. So we've got adding incremental data every day. That's another common use case that's kind of useful to think about. So you don't have a static data set size, right? For this individual, every day they're adding, up to maybe a gig of data. So over the course of months or a year, you're looking at, big change in data set size. Another person saying 5 to 10 gigs per day, and using a combination of SQL, MongoDB, and things like Python, Celery, NumPy, Pandas. Yeah, so that's a nice kind of hybrid architecture there with things like TensorFlow and TS-Fresh for modeling, and things like Pandas and Dask maybe for scheduling and data frame stuff. So the increasing size of compute, while the distribution of data set sizes is stable, has kind of created some interesting dynamics. So some of these things we can now do on a single node, and that kind of changes the definition of kind of small, medium, and big data. People don't really say big data so much anymore, but there's this, we could say something like, data that you can easily work on your laptop is kind of small scale. Data that you could maybe easily work on with a single large machine is maybe medium. And then if we had to define big, we might say, anything big enough that you just can't realistically process it on a single machine. And of course, as we've all learned, although it's great for your, having experience with these large scale data tools, It's great for your resume, and it's great if you're going to be working at like a FANG type company. You're going to need that knowledge. For a lot of more normal day-to-day work, even smaller things within FANG type companies, it maybe makes sense to avoid some of these big data tools when we can, right? Because they involve a distributed compute tax. Right, so we've been working for 70, 80 years now on some magical mechanism that will allow us to treat a large collection of machines as if it was a single machine. And we have a few abstractions that get us into that neighborhood. We have things like Kubernetes, which kind of works at one level of abstraction, things like, say, Spark or Dask or Ray that work at a different level of abstraction. But all of these have some tax in complexity. Right, and I don't need to tell you that. If you've touched these things before, you know that even Hello World on some of these more complicated platforms incurs a lot of overhead and complexity that you'd like to avoid if you can. If you haven't had a chance to do this, be prepared. Like, no matter what any product or tool tells you about magically scaling stuff out, it's not magic, right? There's always some overhead and cost or tax to that. So we want to avoid that when we can. So a lot of times we can avoid some of the large-scale tools altogether, right? We can downsample our data for some use cases and do analytics or modeling there before kind of launching a full-scale project. To some tools I've gotten pretty good at using kind of out-of-core processing, meaning that they can work, even if they're on a single machine, they can work on data sets that cannot fit into memory on that single machine. So an example would be like XGBoost out-of-core support. So if you have a machine and your machine has enough compute resources for XGBoost but not enough storage, that's not a problem. So XGBoost can swap your data in and out and train your tree ensemble that way. And that's just an example. There are other tools that can do that. TensorFlow and PyTorch have data loader patterns for handling, much larger than memory data sets. Scikit-learn has a thing called partial fit. So that's also kind of a batch or incrementalizing training for some algorithms. So there's a lot of tools that we can use for kind of medium data. We're also got a lot of stuff in the Apache Arrow kind of ecosystem working well for that. There's some other data frame libraries that work really, really well on a single machine and can handle large data sets and run really fast. So VAX here is kind of one tool. Another one that's worth mentioning that didn't make it onto this slide, but is Polars. I should probably add data frame to my Google search. There we go. So if you're not familiar with Polars, this is worth taking a look at. It is a data frame. Well, what it says is a data frame library. It's implemented in Rust, but it has Python bindings. So if you're doing Python and not Rust, you can still use it. It is ridiculously fast. And it's definitely worth taking a look at. It's not 100% compatible with some of the other Python data frame libraries, but in terms of performance, it's fantastic. So definitely worth taking a look at there. Now, what we want to do here is these are all, the title of this is about large-scale data sets. And then here I said, well, there's a tax with large-scale data sets, so maybe you can skip those and, use some of these tools and avoid the large-scale stuff. And that's kind of nice if we can get away with it. But of course, we're here because if you're here because at least some of the time, there's no getting around it. You're going to need some large-scale tools, and we want to know kind of which ones and when. So at this point, we're going to kind of transition to looking at a few of those and talking about their kind of strengths and weaknesses. We'll look at some code examples too and kind of see how to put these systems together. So what I did to kind of give us a little bit of a structure to this, rather than just being a laundry list of tools, which is kind of hard to think about, I picked a really generic workflow that we often see, and thought maybe what we'll do is we'll kind of work our way through this workflow from end to end and think about which tools make sense at different pieces. So this is, there are a lot of other applications that you're probably working on that don't fit this exact pattern. But this is kind of like almost like a hello world or kind of a pretty common basic pattern that exists somewhere in most companies or institutions that have large amounts of data. And so we can use it as a kind of a trail or kind of a roadmap And the basic flow starts here on the left, where we've got some data, and this could be a combination of, it could be blob storage, it could be SQL, it could be NoSQL, it could be lake houses, or it could be all of those, all the above. And, we need to find stuff in there, right? That's easier or harder depending on the storage. Then we may need to do some transformation, and that could be things like if we're just trying to transform for processing. So this could be things like aggregating transactions. I don't know, maybe aggregate transactions from customers to generate invoices would be a common, pure transformation use case. But we might also be generating reports from this data, or we might be generating features from this data that we want to use for some AI modeling. So as we move towards the right-hand side of this diagram, things get a little more, there's a few more paths here, right? So we might just transform the data and write it out. That's kind of this path on the top. So that's one place we might end. We might take this data and analyze it and produce kind of reports or dashboards. That's kind of this middle black and white bar chart, kind of in the middle on the right here. Or we might take that as kind of a first step in featureization and use those features to then maybe train some machine learning models or generate reports further on. So we could kind of end up at these different endpoints on the right. And this kind of roadmap makes sense because for each of these places, there are some tools that are stronger than others. So what I'm going to do here is I'm going to switch over to Notebook 02, and we'll kind of start. So, maybe you want to ask a modeling question now, we can do that, or at the end if you want to ask a SQL question, that's totally fine. So whenever stuff comes up, I have one little note here that this, in my little roadmap here, the extracting of the data or locating the data, extracting the data is kind of the beginning of this path. But I understand that there's a lot of stuff upstream from this, right? And we can't kind of have the entire universe of architecture in a single class. Well, maybe we could, but I'm not going to try and do that class. I think that might be a bit much. But we do know that there's ingestion of data, like there's stuff upstream from this where we're collecting data from partners and or customers or various places before it even gets into that lake house. There's also the discovery question. So my part of the company might be collecting and curating this data, but you work in another part of the company, your boss asks you to do something with the data and you don't know where the heck it is. So how do you find, if I say, just find the customers from Canada and India? Well, okay, it might not be obvious where that information is, or there might be, or it might be worse, it might be spread all over the place. It could be that the Canada and India customers are actually in order to get that information, we need to find a bunch of totally separate storage locations and figure out how to merge those somehow. So there are tools upstream from the locating things in the lake or lake house part of the world. We're going to kind of skip those and kind of imagine that we know roughly where this data lives, meaning we've got, so maybe we're looking it up in like a Hive metastore, or we're looking it up in some other data catalog or discovery mechanism. And now we've got either paths or even nicer table names, if we can get away with that. And we need to go and retrieve some data and process that. So for this, there's been, there's the ongoing kind of debate about SQL versus code. I tend to be kind of a fan of everything, meaning I'm not here to say that SQL is better than a data frame kind of API or something like IBIS that kind of unifies things behind a data manipulation API. I'm also not going to say the other thing. I think it depends on your company, your organization culture. But I think we probably all agree that even if you're completely bought into, object-oriented programming and data frame APIs or data access APIs, that SQL is not going anywhere, and it's really critical. So this could be because it empowers other people who are not programmers. So there are a lot of data analysts and management folks that know SQL, and they're not going anywhere. There are some reporting tools where maybe SQL is kind of a common language across these different tools. Like a lot of companies have certain kind of canonical jobs or reports written in SQL, and then they may run those in different systems, but the kind of SQL is the canonical form. And then there's some people that just prefer it. Like there are some things that if you learn how to do them in SQL, like especially around things like lateral joins and stuff like that, it's really nice to learn that once and then be able to carry it to lots of places. So you might say, yeah, I know I could do this using some API in each of my favorite tools, but I'd rather just, kind of learn it once. So SQL is going to stay really important. And what we need is a way to use SQL. We need a powerful engine, meaning one that can handle very sophisticated SQL queries, right? There are a lot of tools that can handle trivial SQL queries, but that's not very interesting, right? In the real world, the ones that we come across at work, are a mess, right? And not in a bad way, but it's not uncommon to come across a 200-line query in SQL that uses all kinds of things like recursion or lateral joins or this or that, we need an engine that can handle that. So we need kind of non-trivial or robust SQL support. There's also a question about where are we getting our data from in terms of data formats, right? So in the relational database world, you don't have to worry about that. You talk to the database owns the storage. But in the data lake and lakehouse world, the storage and the compute are kind of separate. So then we care about which formats we're using and how robust they are. Specifically, in this example we're going to look at, we've got some data that's in Parquet format, which is probably the overall leading format for tabular data, but it's not a complete solution. So there are lakehouse formats that live on top of Parquet, so things like Delta Lake, Apache Hoodie, Apache Iceberg, that may kind of use Parquet underneath, but then add transactionality and indexing and stuff like that. And so we need to kind of take into account, well, which tools can read from these different formats. The main tools that we probably would be looking at would be SparkSQL and Presto. Those are probably the most robust in terms of how much SQL they support and also how well they integrate with these more advanced table formats. There are some things like, say, Dask SQL. Who knows? Maybe in the future that will be able to handle more of these use cases. At the moment, we'll see that Dask is a pure Python distributed compute framework. We'll see that it has some strengths. But SQL and data frame is really not where it's most strong. So there are some issues around there. So for today, you probably would not want to use Dask SQL, or you wouldn't be able to, for a bunch of reasons. If you needed to do really complex processing in a robust way over, say, Iceberg tables or something like that. We'll take a look at just an example using PySpark. And if you're totally new to Spark, then this should be kind of fun because you can see that we can do some useful things with PySpark without really writing any complicated code. If you're already a Spark veteran, you'll be bored because this is not particularly complicated Spark code. So you're not going to learn anything new about Spark right here. But it's kind of cool to see how we can bring Spark in to handle some of this SQL work really nicely. So we can do things like, we've got some sample data in this data folder. So down underneath here, we've got we have a folder here. This is, you can see I've got a bunch of pieces in this California folder, which are, it's from the airline flight data set that you may have seen. And they're filtered down to just some flights within California, which is kind of where that name comes from here. And you can see we can do things like spark.sql and do some simple querying directly over the files. So these happen to be in our local container, but these could be in S3 or wherever else. And this is not the most remarkable SQL here, but Spark does have probably some of the strongest support, especially when we start getting into these formats like Delta Lake or Iceberg, and the newer versions of SparkSQL that can allow you to do things like upserts or conditional merging of data, in addition to all of the, or deleting individual rows, which are, kind of a little bit more feature rich than the systems a few years ago. We can, look at slightly more interesting queries, like maybe if we want to look at things like average delay for flights that have, for cities that have more than 500 flight records in the system. So if we wanted to say, if we have records on all of these flights, we wanted to say, well, which are the most troublesome airports to fly out of? Which are the ones that have some of the biggest or the smallest average delays? We might want to do some query like this, and we might have this kind of halving clause here because we might want to exclude some airports that are really, really tiny. So there are regional airports that only have a flight, one flight a day, and that's going to throw off the statistics. So maybe we do something like that. And this gives us a view of what that looks like. It looks like in this data set, Palm Springs, that's this one up here, Palm Springs was maybe the worst behaved. This is mean delay in minutes. It looks like Palm Springs, then Oakland, San Francisco, and then ACV. I think that's Eureka. But anyway, I know you're not here for to discuss flight hassles in California, so the details of this are maybe not super important. But the how we can put this query together and how we can run it, that's pretty nice. And then, of course, Spark makes it really easy to go and transform this data. So what we're looking at here is how we integrate different tools. So one common use case is a data engineer may need to go and locate some data and refine it in a particular way, but then they're going to hand it over to a data scientist, and maybe the data they pass over is actually small. And so maybe once we've done the extraction with some large-scale data tool, we end up with a small collection of data, and we can hand it to our data scientist partner as like a CSV file. I don't really recommend CSV files for a bunch of reasons, but people still use them a lot. So we can see an example here of how Spark lets us really easily, say, run a query and then rewrite that data into another format. So we can do that here. Let's see, there's a question, are the materials of this class available in a repo? They are. So let me find that, and I will give that link out. Yeah, this is a public, these notebooks live in a public repo here. And I'm just looking in my, on my other screen, I'm looking in my GitHub to find the link, and I'll put it in the chat window. Yeah, so that's this. Just moving some windows around. That's this link over here. So if we click there, well, that's on the wrong screen. But yeah, so there is a GitHub repo here that has the notebooks and the data and stuff like that. So you could use this if you wanted to update this or change things around. And feel free, some of this, as we're going to see, some of this code that we're going to look at, especially around Ray, is not the latest APIs. So so kind of take some of this with a grain of salt. But you're absolutely welcome to use this material if you want to share with other people in your company or at a meetup or whatever. Like, it's you can do whatever reasonable stuff you want to. With this, I guess maybe you're not supposed to sell it to a company that competes with O'Reilly, but other than that, that's not, I'm not too worried about it. And then here, this last cell here, where we're doing the Linux head command here, just kind of showing that we did manage to take our refined data set and rewrite it as CSV in this kind of hypothetical scenario where we're trying to pull out a small amount of data from this large collection and then hand it off to someone who maybe wants to do further analytics or modeling. So this is let's see, close that tab here. So this is kind of a quick look at the feature extraction end of things. Just to, since things, Spark and Presto probably have the most robust SQL support. I'm going to share some links for some of these other tools I've mentioned, because I know I'm mentioning a bunch of stuff kind of fast, and if you haven't seen these tools before, they might be, you might want to look into those. So the most famous of the Lakehouse formats is probably Databricks' Delta Lake format. So I'll throw these links over here in the chat window. So this is the homepage for Delta Lake. The big news on Delta Lake is that until this past summer, the only way to get the most advanced features with Delta Lake was to be a Databricks customer. So if you were using Databricks, that was great. But if you weren't, the code wasn't available. It wasn't open source for some of the fancy features, and it wasn't even for sale. You couldn't license it independent of Databricks. That's changed. So this past summer, Databricks open sourced kind of like the full version of Delta Lake that includes things like Z-order indexing, and that makes this a kind of a much more interesting project, because you can now, you have all the power in the tool, and you can do whatever you want with it in terms of integration. And if you're using Databricks, again, that's great. But if you're not using Databricks, then that's fine. You can use it with other stuff. And this Delta Lake format is fairly battle tested at this point. It's probably about 4 years old, and it's been used in lots of really large customers in their Databricks deployments. So it's got a lot of the kind of kinks and challenges worked out. So I used to be a little more hesitant about recommending Delta Lake because it wasn't fully open source, but now it is. So that's definitely one to look at. The two other big ones are Apache Iceberg. So this originally came out of Netflix. This is kind of developing really, really quickly. And I'll throw this link into there. I'm not going to go into detail on all of these because, it's kind of a fractal. Like all technology, it's kind of fractal, right? At each point, there's lots of options. If we go way down the rabbit hole into the details, we'll never, we'll kind of get lost, and we'll never finish. But I will share these links. So there's Apache Iceberg. The other one is Apache Hudi, spelled Hudi. And if your organization doesn't have a strong feeling for one of these or hasn't made a decision yet, these would be the ones you'd want to probably do some evaluation and comparison with all three of these, because they're all good projects and they all have strengths and weaknesses, and only you can kind of decide what's right for you. But they'll all work with things like the Spark and the Presto engine, along with other stuff. So those are some of the formats we might be looking at. And again, these are things that live on top of a format like Parquet and add transactionality, conditional merging like upserts, indexing, row-level operations like delete where. So things that traditionally were not kind of accommodated easily in large-scale data, these kind of data lake formats. But we can now do it, and that's where this term lakehouse comes from. It's like this hybrid of a data lake because we've got a bunch of files, but it also has some data warehouse capabilities because we've got things like schemas and ACID transactions and stuff. That's a great question. Any of the tools I'm covering have support for graph-based big data? I would say none of them have it as a first-class use case. And that's a great